Welcome to the sixth lecture on NSM course on OpenACC. We so far looked at the compute constructs, parallel kernels, and then we also looked at loop, which is again related to the computation, but typically considered to be used primarily for distribution of work, and that's why it is also called as a work distribution construct. What we have, so we have looked at the compute part, but we have not really looked at the data transfer. And that is one of the very important aspects when we deal with uh, discrete GPUs, which have their own separate memories, and therefore the data transfer starts coming into picture, and the cost turns out to be high many times for this communication. So it's imperative for us to optimize this cost, and for that, OpenACC supports certain constructs. To understand that, let's take one very specific example. The example that I'm going to take is for vector addition. Right? So this is a simple program which you would like to write. So in sequential setting, we'll just go over two vectors and we'll sum them up into another vector. Right? So therefore, the sequential code, let's say C-like code, turns out to be, as far as main is concerned, I'm going to use these ABC arrays of some size n. I'm going to initialize A and B using two functions, let's say init. And then I'm going to use an add function, which sums up the associative elements of A and B and writes it to the, C of I equal to A of I plus B of I. Finally, I might want to print it on the CPU or do some other processing on the CPU. That's fine. And I also pass this n as a parameter, although it's a hash defined. So even if you access it directly in the functions init and add, that is also okay. Right? Okay, so this is our basic vector addition code. Right? How does the code for let's say init and add look like? So the initialization which I want to do as far as parallel initialization is concerned, for this for loop where I am assigning some value, initialization could be arbitrary. I could be using arbitrary functions corresponding to how I want to initialize this particular array x of I. In the context of OpenACC, I'm just going to use ACC parallel loop, and that is going to take care of parallelizing this particular code. Okay? So it is very simple from the perspective of whatever we have studied with respect to the compute constructs. And this seems natural that I'll parallelize in this manner. Can somebody, yeah, I request everybody to write down how the add function is going to look like and what pragma will you use there. So please think about it, spend a few seconds. Okay, so the add function, and you must be thinking about this, that it also should look very similar to the init function in the sense that there will be a for loop going from 0 to n, and then there will be a statement which just says C of I equal to A of I plus B of I. Right? And as far as the pragma is concerned, that is again going to be exactly the same as in the init function. Right? So this seems a very nicely parallel, naturally parallelized program for vector addition. Okay. When we give this program to the compiler, anyway, by any chance, are there any questions so far? Okay. So when we give this program to the compiler, what does the compiler do? Well, it's going to give us this information with respect to what all happens with respect to wherever there is a pragma, it is trying to perform some operations, right? The OpenACC compiler is going to say that in init, I see that there is a parallel loop, so I'm going to generate a Tesla code. I see that it is parallelizable, so I'm going to parallelize it and so on. Along with that, there is some additional statement which we have so far ignored in our earlier discussion, which it says. So it says that I am generating an implicit copy out for x of something, x of opening rectangular parenthesis colon n closing parenthesis, right? If not already present. Right? So we'll try to make sense of this, what this means, and why this particular output comes out. But in general, this copy out means that it is trying to copy the array x from GPU memory to CPU memory if the copy doesn't exist already on the CPU. Okay. And in this case, since x of I is going to be assigned a value here, therefore on the GPU, therefore the CPU copy is not going to be in sync with the GPU copy, and therefore that copy out is actually going to happen. So this, if not already present, is really not required here. That x is going to get copied, and what is x? Well, it is going to be either A or B. Okay, which means that after A is initialized, it is going to get copied back to the CPU. After B is initialized, it is going to get copied back to the CPU. This is what this copy out is going to convey to us. And as you can imagine that this is not really something which is optimal. The reason being that the add function is also running on the GPU. I mean, as far as this for loop is concerned, that is also running on the GPU. And therefore, I don't really want A and B to be copied back to the CPU. I actually want only C to be copied back to the CPU, right? Because I want to make use of it, let's say, later on the CPU. Okay. So this is one aspect which the compiler tells us, that there is some redundant copying happening which we would like to avoid. Okay. For best performance. Further down, for add also similar thing happens, where it is going to say that it's going to generate an implicit copy out for C. In this case, that is all right. The reason being, I am planning to use C on the CPU. But what if I was not? Maybe after add, I want to do some other operation onto C. In that case, again, this copy out is going to be redundant, and therefore I should be careful about this particular aspect. Okay. After this, it also says something about copy in of B and A. Right. So copy in of B, this syntax we'll understand what that means. But essentially, it is trying to copy these many elements, let's say n elements of A and B. Copy in means it is copying from CPU to GPU. So this copy in, copy out are with respect to the accelerator. So it wants to copy in A and B. So the order doesn't matter in this case, the copy out and copy in on line 10 that it is saying. It doesn't mean that first it will do a copy out and then it will do copy in, not like that. It will, if it has to do copy in, that has to happen before this loop parallelization begins, because A and B are actually read inside this loop on the GPU, and the copy out is going to happen at the end of this loop. Okay, so don't worry about this particular order of these two statements. Is this required for add that the initialization, sorry, the A and B arrays or vectors should be present on the GPU? Well, yes, it is important, but it is not really required in this case, because A and B are actually on the GPU. How do you know that? Because I have already initialized those on the GPU. And therefore, this is kind of redundant copying in, which might actually happen. Thankfully, if not already present, we'll take care of that. So if it is already present, hopefully it will not copy. But I would like the compiler to know that I already have it on the GPU. I don't need to really, you don't need to worry about even thinking of copying. Right? So that is what is the expectations from the program. Right? And not all of these can be identified by the GPU or the compiler automatically, that this particular data item already is present or this particular data item is not present. This is not always feasible for the compiler, because there is a lot of pointer related operations that will come up when we are dealing with arrays and matrices. And therefore, I mean, some particular pointer might be pointing to some row of a matrix and so on, right? So there will be, and I might deallocate some memory at some point in time, I might allocate, etc. So the pointer analysis itself becomes a challenging problem for the compiler. And therefore, it is not always possible unless the program is reasonably structured, where I say that, oh, this is all A of n, B of n, C of n. This is all, I know that A's size is n, right? The plus n is hash defined, so the compiler can figure out, okay, the value of n is this much and I can copy this much data and so on. But in general, the compiler, we do not know exactly which data is going to be happening on the CPU, which on the GPU, and so on. Right? There might be if-else statements which are dependent on the input parameter. And if that input is going to come at runtime, the compiler can't figure out what is going to happen, whether the if block will execute or the else block and so on. And therefore, the dependence on the further statements after the if else block will also be difficult to identify what will be that effect, because if blocks effect will be different, else blocks effect will be different. Okay. So I hope the problem is clear, that we would like to optimize this data transfer as much as possible. So let's try to do that. For that, we have to go back to our earlier slide where we said that the CPU and GPU memories are separate. They have different DRAMs. Room number 25 in, let's say, computer science department or electrical department or materials department. These are all going to be probably having the same number, room number 25, but they are all different. So you cannot really access, if you want to attend a seminar in room number 25, you need to know which buildings room number 25 I am talking about. In a similar manner, if I am accessing something on the GPU, thinking about that the address is the same as I was obtaining from the CPU, that is not going to work. We'll have to copy that data into the GPU memory and vice versa. Okay, so they have different RAMs, and therefore a variable in CPU memory cannot be directly accessed by a GPU as well as vice versa. And OpenACC automatically copies this data across CPU and GPU, and the programmer can help in optimizing the communication, right? So this is what we had said some days ago, and today is the time to inform the compiler how to help in optimizing this communication. And that is given with this data construct. What does this data construct do? It says that I am going to tell you whether to copy this particular data item or not, or whether this particular variable is already present on this device or not. Okay. How do I specify that? The syntax is similar, hash pragma ACC data followed by certain clauses. The clauses are going to essentially help us specify all this information that I was just talking about. This particular data part can also come along with parallel as well as kernels as well as serial. So even their generated code can actually be optimized by these programmer related clauses specified, the data clauses that are specified. The first clause in that is copy in. That means if I am entering a parallel block, which is going to get converted into a kernel, whether that kernel is running sequentially or parallelly, that doesn't matter to me. But if I am entering a pragma ACC block and I encounter this copy in clause for the data, then I need to copy whatever is the data that is on the CPU given in this copy in clause on the GPU. Right? So that is what it says. So in general, the way this copy in block works is that it checks if a variable is already present on the device. If it is present, it doesn't do anything. If it is not present, then it copies it. Right? For copying, that data should have memory allocated on the GPU, which may or may not always happen. If the memory is already allocated, then copying is only going to copy the memory from CPU to GPU. If the memory is not allocated, then memory allocation will happen, and after that the copying is going to happen. Okay, so copying is actually a very small, handy way of specifying multiple things. Whether the variable is already present on the device, if it is not present, whether there is memory allocation done for that particular variable. If memory allocation has been done, has it been copied from CPU to GPU already? If it is copied, then it is not copied again. But if it is not copied, then this gets initiated. And then it initiates a copy from host to device or from CPU to GPU. Okay. Any questions on this copy in block, copy in clause?
Sir, let's say the variable is present on both sides. By both sides, I mean device and host. but then the data is not synchronized. Say let's say on GPU it's some 5. I'm giving random data, and on
Correct.
CPU it's 1. If
Right.
then it encounters a copy, will it update?
Yes, it will always update. So the compiler does perform this check that whether it is updated on the GPU or not. Whatever is the latest write from the CPU, whether it is already whether it is copied already to the GPU or not. If it is not copied, then it is going to copy. So that way we are safe.
Okay, so this also acts as a synchronization point, is it?
Does this act as a synchronization point between CPU and GPU? Not necessarily. The reason being that this copying can be done asynchronously. I don't know if it, so I mean, I'm thinking from the perspective of CUDA. CUDA supports both synchronous copying and asynchronous copying. CUDA memcopy and CUDA memcopy async. These are the two functions. I am not sure which one is used in this particular OpenACC implementation. But if it is async, then it's possible that it will not act as a backup.
Okay.
Okay, so this part is fine. And then you can think about what will copy out do. It's going to be copying data from GPU to CPU, right, out of the GPU. And this needs to be executed not at the entry, although you will write it at the top of the for loop. This copy out is going to happen at the end, right? So think about copy in as a constructor and copy out as a destructor, right, which gets executed at the start and end of a class instantiation. So this copy out clause gets executed only at the end of this particular block, right? So again, it checks if the variable is already present on the host. So being already present is not necessarily only about whether the data is, whether the memory is allocated or not, but it is also about whether it is in sync or not. If it is not, then it initiates a copy from the device to host. And what should be the last one? What should be the last point that copy out should do? So it should also deallocate the memory, right? So in copy in, we are allocating the device memory. So in copy out, we also need to deallocate the device memory. And yeah, so as Suru was also suggesting. One place, right? So although this syncing across CPU and GPU happens very nicely, and the compiler generates code corresponding to checking if there has been a copying and do the copy if required and so on. If it gets modified on the CPU, do the copy on the GPU and vice versa. One place where that optimization doesn't work is that when the CPU GPU copies are written at two different times, but the data turns out to be the same, right? So let's say that I have written something into the CPU memory, CPU array, and now there is a copy in clause, right? So although the GPU memory might contain exactly the same values as in the CPU memory for some reason, it will still do the copying because there was a write done on the CPU to these memory locations. Right? So it doesn't look at the values, it just looks at that there was an operation of writing and therefore it should be copied to the other device. All right. So knowing this basic information about these data clauses, and these are the two primary constructs which are going to be helpful for us develop OpenACC programs further. Let's come back to vector addition. So what I'm going to do here is that initialization, the two initializations and the add, I'm going to push inside a data clause inside this block of code. The allocation of the arrays is still on the CPU outside this pragma, and then making use of that is also outside. Within that, what am I going to say? I'm going to say that hash pragma ACC data, copy in A and B, and copy out C. As long as I say that, then that means that A and B are going to get copied to the arrays from CPU to GPU. And then once C is available, that is going to get copied back to the CPU bank. Okay. Any questions on this part? Anybody sees any issues with this particular piece of code?
Sir, one thing.
Yeah.
In this thing, you are copying in A and B, but you have then anyway declared C on the device first, right? On the host first, right?
Sorry, read that last part. But about C what?
Yeah. So the C is now when we are encountering this hash pragma SEC data, the C which is inside that thing, right? So that is the moment we do add C ABN, which C will it refer to?
Which C it will refer to?
Yeah, because see, we haven't done a copy in of C, right? So
okay.
the thing.
So why will we require copy in of C?
See, because in the add we have C of I is some A of I plus B of I, right? So which
correct.
C, that C of I will refer to which C?
Okay, good question. So when we have this C of I in this case, we want, so what Dhruva is suggesting is that for the memory access, we need to be careful about that C should be available on the GPU. He's not saying, I was wondering if he is talking about the array C which is already there on the CPU, that should also be copied. But yeah, so you are right that as far as copying in is concerned, as far as read write are concerned, we need to read A and B and we need to write to C, but that memory should also be available. So which one it is going to say, because we have not really said anything about copying in of C. If we have not said anything about copying in of C, and that is actually generating a parallel code, then the compiler is anyway going to create a copy of C on the GPU. Right? Recall that earlier when we had not specified this pragma, all of A, B, and C were actually getting allocated on the GPU. Right? Now, because of this copying in, as far as A and B are concerned, those are definitely going to be copied, so that is fine. But we have not said anything about C, so it is going to anyway create the copy of C on the GPU. That is by default.
Okay, so by that logic, is there any point in separately copying in A and B? Because in any case, we are going to print the C variable, right?
Okay, so let's say that I am not going to copy in A and B, right? So I specify this hash pragma SEC data, copy out of C, right? I don't say, specify anything about copy in of AB. If that is the case, it is not going to copy A and B. So there is difference between AB and C, although I have specified only these two constructs so far to you, and that is where the confusion is coming into picture. What we have in case of copy in are multiple parts. Multiple parts meaning first is the check, if it is already in sync. Second is whether memory is allocated for it. And then the third one is about copy. So if I do not specify it for A and B at all in this case, actually, no, sorry, I will take my words back. It's not that copying of A and B is not going to happen. It will happen because we have specified hash pragma SEC parallel loop for the initialization of A and B. So that at that time, A and B are going to get copied, and A and B are also going to get copied back at the end of the parallel. So the advantage that you get by specifying this copy in A and B is that you don't do copy out of A and B until it is required. So our original program, which did not contain this clause, but which contained only this dimly defined right-hand side blocks, right? So we had these parallel loops. There we were copying A and B, as well as we were copying back A and B at the end of initialization. That is going to get avoided because of this data clause, which is spanning multiple functions which are running on the multiple kernels which are going to run on the GPU. Is that okay?
Okay, so you mean to say if this copy in A and B was not there, the end of the data region, we will be doing an unnecessary copy out of A and B,
Yes.
in spite of the fact that we have written copy out only C.
Copy out only C is written, but copying out code is going to get generated for the parallel loop, which is present in the other function, init function as well as the add function. I'll also show you the compiler but I will not have it for the case you are mentioning. But yeah, we can check that. I think.
Okay.
So let me just spend a few seconds thinking about your question also. So hash pragma ICC data, if I do not have copy in AB, I just have copy out of C. Won't it copy or will it copy A and B back to the GPU? Yeah, back to the CPU. Hmm. Okay, that is not very clear to me. Yeah, so I take back my words. It's not clear to me that it will copy A and B back to the CPU. I'll have to check the compiler output for that.
Okay, no problem.
Yeah. Sure. Okay, so sounds good. So we had, so since we are reading A and B, we are doing copying of AB. And since we are writing to C on the GPU, that is inside the add function, we just have the copy out of C. We don't need a copy in of C because C is not really getting read. I mean, whatever is C of n here, that is not going to get really used inside the GPU. So we don't need to copy in C. So that part seems to be okay.
Sir, I had another point. What
Yeah.
if we did this int A of n, B of n, C of n inside the data region?
If you do that inside, then we won't be able to specify these parameters here.
Okay, so if we don't specify that, like, let's say my program looks like hash pragma SEC data, copy out C, and then we do int A of n, B of n, C of n inside that. Okay, no, scratch that. Let's say we keep int C of n outside, but we put int A of n and B of n inside the data region.
Right.
So,
We just have this copy out of C.
yeah.
So what will happen? So init an, that is going to
See, if we require A and B after doing the vector addition, that's fine. We have to do it outside. But
yeah, part is
if
okay.
we don't require it, that's why I'm saying that so the process of initializing A and B should be done on GPU itself only.
Yeah, that part seems to be okay. And I think this also will refer to the earlier question that A and B, whether those are going to get, since we are defining these inside here, initialization will have a pragma parallel loop, so it is going to get copied to the GPU anyway. B will also get copied to the GPU. Whether it is going to get copied back from GPU to CPU, yeah, that I don't know. Yeah, so it will have the same effect as currently we are doing.
Okay.
Right. All right. So this seems to be good. There was something else I wanted to convey here. Okay, I think that point will anyway come. So if I look at now, after specifying these copy in and copy out operations, clauses, what does the compiler say? The compiler says that it is generating implicit copy out of this for init and add, but now it is going to say something about main also. Earlier main did not have anything, any OpenACC pragmas. Now since it has, it is going to say something like generating the copy in of A if not already present, and copy out of C if not already present. Similarly, copy in of B if not already present. Right? So this is what we anticipate the main function should, the pragma ACC data should do. And when we look at the code corresponding to this, we would like that these implicit copy out in the init and the arr functions, or copy in and copy out, these you don't need to check, because I know that in case of init, I have already copied in, by the time I reach init, I have already copied in A as well as B. Similarly, when I am in add, all of these are already present on the GPU. So I don't really need to even generate a code to check if it is present or not. So this can be specified by this present clause. What it suggests is that this particular variable, this particular vector in this case, is already present on the GPU. You don't need to worry about copying it in. In a similar manner, the same thing happens for ABC variables when I reach the add function. However, we have to be a little careful about this present clause. The reason being that if the programmer specifies the present clause, then the compiler will not generate code for checking if it is already present or not. As can be seen, that these get removed from the compiler output as soon as I specify the present clauses. So this is the advantage. Otherwise, what will happen is that the compiler will still generate code to check whether X is present or not on the device, which we again would like to avoid, because we have already taken care of that in the data clause. Okay, so let's look at the flow again. We have A and B allocated on the CPU memory. Then I'm going to say that copy A and B to the GPU memory at the entry of this block, and at the exit of the block, copy out C from GPU to CPU. When I reach the initialization, I know that A is already copied in, and therefore A should not be even thought of checking. I mean, the compiler should not think of checking that whether A is present. So I specify that by specifying that A is already present. Then I go to init of B. B is also already present is what the programmer specifies. When we reach add, at that time I also specify that all these ABC matrix vectors are already present on the GPU, and therefore you don't need to think of checking if it is already present or not. And if not, and that is going to help you reduce this communication to exactly what you would have otherwise done if you had written this manually. All of this copying business, if it was in your hands, then you would have copied things minimally. So that is what is essentially going to happen. And at the end of this block, whatever is written in C and not A and B are only going to get copied from GPU to CPU memory, and therefore it will also reduce the communication with respect to A and B arrays. Right? Okay. Any questions so far? All right. If there are no further questions, then I'll show you what happens when we execute the two programs. Right. The first program was without any data clause. Right. We just had the pragma parallel, and then the second one was with using the data clause inside main, and I get some profiling output done. So there is a lot of other data which is there on the slide, but what we need to focus on are these red numbers. Right? So as far as the original code is concerned, the initialization took 48 microseconds, and well, I will also say that the data copy out transfers also suggests that there were two copy outs done, one for A and another for B, right? And then add was done, so that took around 25 microseconds, and we can see the data region. Yeah, so the copying in was done twice and the copy out was done once. So this copy in was for A and B again, and this copy out was for C. So as you can see, there is this redundant copying happening, copy in of A and B, and this copy out of A and B, which we are essentially avoiding by specifying this data clause. So when I specify the data clause, the initialization takes almost 0 seconds. This 0 doesn't mean, it just means that it takes very small amount of time. Similarly, add also doesn't take much time. Main, now since it has a pragma, we are going to specify some work to be done. In fact, the data transfer is going to happen there. So there is copying in happening twice, one for A and another for B, and copy out happening once, which is for the C variable. And the total time turns out to be around 48 microseconds, which is still better than overall 0 plus 0 plus 48 is still better than 48 plus 25. So we avoid some data transfer in this case. How do we get this particular output? Well, there are multiple ways in which you can profile your code essentially. You can use a clock function, you can use a get time of day function, and using these, this checking of time can be done in a similar manner in OpenACC programs as in C++ programs. So we can use any of these functions and measure the time. Specifically, this particular output is obtained with the PGI PGI environment variable. So we can specify this PGI ACC time as environment variable on the Linux shell before we run this a.out or the program which contains this OpenACC program. And it automatically generates this profiled output, which can be very helpful, can be very handy for you to check the overall profile of this execution. Okay, so I'll move ahead from here. There are other data clauses which I didn't specify. We just looked at copy in and copy out and then present. But there are variations of these. For example, if you want to, many times it so happens that CPU is doing some operations, there are some arrays which are populated, and then you want to offload it to the GPU, do the computation, get the result back, and so on. So instead of specifying copy in ABC, copy out ABC, I can just say copy ABC, and that will take care of both of these, copy in and copy out. And then there is also this create, which is created on the device but do not copy. Right? So this can be very handy, especially in our case where C variable is not really getting copied from CPU to GPU because it is actually getting initialized on the GPU. So in such cases, we can, instead of specifying copy out of C, we can as well specify create of C. Right? And that will take care of creation of that particular variable. We'll have to still specify copy out of C, which anyway is required in this particular case. So this create pragma is useful when you have some sort of initialization is happening directly on the GPU. So there is no real dependence on what the values are on in the CPU. Okay. The opposite of create is the delete, which is also implied by copy out, where we delete that particular variable. So you can just specify it explicitly in case you want. Okay. Any questions so far? All right. So while specifying the data range of this, now we are going to get into the syntax of what we can specify inside this copy in, copy out, present, create, not create, but copy, etc. And that specifies the range of elements that you want to copy from one device to another. So if you don't specify anything, so if you just say copy of A, then the compiler should know the length of A. That is not always possible, as we discussed. If it is a compile time constant, which was what was happening in our program, then it is okay. But otherwise, if you don't, so that's why we could use copy in of A, B, and copy out of C, because that A of n, B of n, C of n was already there as part of the code, and compiler was able to figure out because it was n was hash defined. In general, we can specify A rectangular parenthesis colon closing rectangular parenthesis, and that also means A, and that also means A of 0 to n minus 1 in the context of C, C++, or 1 colon n in the context of Fortran programs, where n is the compile time known length of it. Okay? So only if the compiler knows, it will do this correctly. If the compiler doesn't know it, then specifying only this or only this is dangerous. If the compiler is unable to figure out the length, it might just copy one element of that array. I repeat, if the compiler is unable to figure out the length of the array, it might just copy only one element of the array. That is what happens on my implementation of OpenACC compiler. But I mean, in my machine, but in general, you might face some trouble with respect to that. So it's always a good idea, unless it is static time, compile time known constant, you specify it very explicitly that I want to copy 0 colon n minus 1 or 0 colon n. Actually, this should be 0 colon n and not 0 colon n minus 1. Yeah, this is specified as the length of the array and not the last index of the array. And there is also some distinction. We are talking in the context of C++, where this second parameter is actually the length of the array. In contrast, in Fortran programs, the second parameter is actually the end index. Okay, so this is okay for Fortran program, but not for a C++ program. Okay, so if the compiler doesn't know, then the programmer needs to help, and that is where A of 0 colon n will come into picture, and that is what we have to provide. So we have to specify explicitly hash pragma data and copy in A of 0 colon n, not n minus 1, and copy out C of 0 colon n in the context of C programs, and 0 colon n minus 1, 0 colon n minus 1 for Fortran programs. Similarly, I can, by the way, this can be an arbitrary expression. It's not necessarily that should be a very simple expression. You can make it as complicated as you can, and the OpenACC compiler will still work. So you can copy a full matrix completely like 0 colon n, 0 colon n, or you can specify a subrange 1 colon n minus 2 or 3 colon 5 into m, something like that. For this is just a hooked up example to showcase that arbitrary expressions are allowed. But yeah, you can just copy only a submatrix of this matrix into the GPU memory. All right. Yeah, so this is what I wanted to convey, that while all these clauses are uniform across C++ and Fortran, only at this particular place there is a distinction between the two, that in C++ the syntax is array followed by start colon length. That's why we have to write 0 colon n and not 0 colon n minus 1. Whereas in case of Fortran, you have to write, the interpretation of start colon, the other number is end of, the last index and not the length. And therefore, if you have to write with 0, we'll have to write 0 colon n minus 1. Or since in Fortran you can start the array length from any index, you can as well provide array of 1 colon n, right, where n is the last index. Okay, this is the one aspect which the Fortran programmers should be aware of. But otherwise, there is no distinction as far as other clauses are concerned. Pranshu is saying, can we copy any number of elements of the array, or is it necessary to copy the whole array? Yes, you can copy any number of elements of the array by specifying this syntax A of array of let's say starting index colon number of elements you want to copy.
Sir, can you just go back one slide?
Yeah.
Continuing with Pranshu's question, so I think what he means is, let's say we have m 0 colon n 0 colon n. Can we have, so it means that it will copy an n square length of matrix, right? Say,
Right.
can we copy something like an alternate elements like 0, then 2, 4, 6, 8? Is there any syntax to do that?
Yeah, is there a step size given? No, step size is not given. I think it will always be contiguous.
Yeah. So coming to this contiguous now, on the GPU memory, is it a contiguous physically, the arrays?
On GPU memory,
Yeah.
uh, on GPU memory, is it going to be in a similar contiguous manner? Um, yes, and in fact, more so that yes, it is going to be a contiguous memory, is what I believe. For vectors, I mean, for single-dimensional arrays, it doesn't cause any problem. For a matrix, whether it is going to be contiguous. I mean, I can imagine that one row will be contiguous or one column in the context of Fortran, but whether multiple rows or multiple columns will be contiguous or not, that I am not sure.
Okay. And a little bit on this, is it possible to do pointers in the GPU memory?
Yes, it is possible to do pointers in the GPU memory as well. And we do have one slide corresponding to that. But yes, so for example, you can copy pointers from CPU memory to GPU memory, but unfortunately, it will still point to the CPU memory. So we'll have to take care of the pointers explicitly by the program. Okay, so that seems to be fine. And this is what we discussed. Yeah, so let's come to a slight variation of this vector addition, and I'm going to ask you to write down the code now that you have looked at this vector addition. So I want that this element-wise matrix addition be done, and we can assume it's n cross n square matrices. So you are given this A and B, and what you want to compute is C equal to A plus B, where we are. So nicely things are parallel in this case, because you can just copy, you can just think about adding corresponding elements from A and B and writing it to C of ij, where each thread is going to perform these operations completely in parallel. Right? So one advantage of this is that it also scales well with the input size on many core accelerators as far as number of threads is concerned. So I request all of you to spend some time thinking about how you will write the program, and just write out either in your copies or online. Okay, meanwhile, I'll take this question. Swapnil is asking, addressing wise, it may be, but physically may not be. It depends upon MMU in practice and system condition at the time of execution. But mostly it remains in sequence as system finds contiguous space for small sizes. Mm, sure. Thanks, Swapnil, for this. Yeah, the reason why I was not sure about this contiguous part is because you may not actually be even copying the contiguous chunk. For example, when we said that from a matrix we can just take out a submatrix, this submatrix could be somewhere in the middle, and therefore the memory that you are copying is actually not really contiguous on the CPU itself. And therefore, whether it will be contiguous on GPU, I'm not really sure. But maybe what you said, I am not aware if this happens. But what you say, it's possible that whatever you are saying is likely to be happening. Thanks for that. So while we are working on this matrix addition, um, yeah, Swapnil says you are right. Inside GPU, it works like caches. Sure. Yeah, so while we are working on this matrix addition, I request everybody to also think about if there is some difficulty you are finding in parallelizing this or identifying what are the exact clauses which should be used and so on. And if there are any questions, if something is unclear, feel free to ask.
So for this matrix addition, should
Mhm.
the pragma be hash pragma ACC parallel loop collapse to copy in AB, create C, copy out C?
Yes, that seems to be reasonable. All right, I hope others have also tried it out. And since there are no further questions, I'll move ahead from here. You can actually take a look at this matrix addition in mat.c. All these codes are available on the course webpage. And essentially, what Dhrubajyoti was suggesting, exactly the same code is there, except that I'm going to add this present clause in the add as well as the init. So assuming that the rest of the code remains the same on the similar lines as the vector addition. Uh, so we have these two loops and c equal to a plus b. So I'm going to just specify that these are present, and since I want to help the compiler in this case, I'm going to specify completely 0:n, 0:n for ABC altogether. The same thing happens for the init, where again I can specify that the matrix that I'm passing as a parameter for initialization, essentially A and B, those are also present. And why these are present is because of the data clause, which is there inside main. And that data clause says create ABC and then copy out C, right? You can as well say create C, that is also okay. Uh, Yeah, so I have not specified create C here, but that should also be all right in this case. But yeah, create C is probably going to be better. The other thing that Dhrubajyoti was mentioning is about, can we specify collapse to here? So although I have not added on the slide, but it is there in the code mat.c that collapse to is likely to give you better performance in this case, because these are likely to be very parallel. These are not likely to be, these are definitely very parallel operations. So collapsing the two loops is going to be helpful in both initialization as well as the add. Okay. Swapnil says create and copy out combo fails with GCC OpenACC compiler. Oh man. Uh, that's a little strange. Anyway, just those of you who are able to try with PGCC compiler, please try this out. Uh, but it's a little strange that why it would fail. The reason being that, I mean, one can think of a use case where you want to create as well as copy out, right? So, for example, our C equal to A plus B uh, operation, I would like to create C directly on the GPU and then copy it out from GPU to CPU and deallocate it. Right? So that is the only use of C. So I am not sure why this combination is disallowed. But anyway, I hope this improves. Operand in create cannot be in copy out. Operand in create cannot be in copy out. Yeah, that's what I was suggesting. That in general, even in our example, we should say that okay, create AB works and then copy out C works. Um, okay, that's a little strange. Why, okay, so copy out is not allowing create to happen for that variable. I don't know why that is the reason why that behavior is there. But if it is not working for OpenACC, GCC, my feeling is it might not work for PGCC also. Right? So, Dhruvadyoti, if you have access to Aqua cluster, you might just want to try out if this also gives error on the PGCC compiler. My guess is if it's giving it in, okay, Swapnil says, similarly, create a copy out a fails from lu1.c program. I see. I see. So
What's this LU1.c?
that is another program, this LU decomposition program, which is there in the other code. Okay, so Swapnil, thanks for trying this out. But yeah, so this we have verified with the PGCC compiler, but I don't know if okay, so if it is there in lu1.c, then that means that it should be working on the PGCC compiler. Okay, so Himanshu also agrees that it's not working in GCC. Interesting. So that conveys that copy out is somewhere internally allocating the memory for that as if there is create, but doesn't seem to make sense, but yeah, I'm not sure.
So you mean to say this create and copy out together for the same variable works for PGCC?
Right. Yeah, for the same variable. The way you were also doing it for the matrix addition.
Yeah, that seems reasonable. I will create and I will copy out.
It's reasonable, but yeah, it's a little surprising that GCC is not working with this. But anyway, we'll discuss this as I finish these slides. I think we have half an hour for discussion. So let me just finish up this data part. So yeah, so as far as the main is concerned, we again can specify this SEC data create of ABC and copy out of C. On PGCC, I think this should be working. Yeah, on GCC looks like only AB can be specified here. Okay, so one homework is you can try optimizing matrix multiplication. So we have this 3 nested loops IJK, and you want to specify the data clauses as well as probably the copy in, copy out clauses and the present clauses at appropriate places. So either you write everything in main, in which case all of this is anyway going to come together, or if you can use these functions, then it will also kind of give you a practice of how it needs to be handled across functions, right? So, so you can write it either way. And although we have that code available on the course web page, but still before looking at that code, my suggestion is to try it out yourself. Yeah, so let's come to this last part, which I wanted to cover, which Dhruvadyoti had also asked, that can it work with pointers? Yes, if there are pointers, then you can also copy the pointers. But by default, the copying is something called as a shallow copy, right? Which means that if you copy a pointer from CPU to GPU, and on CPU it was pointing to some memory location on the CPU, then after copying it, the GPU pointer will also start pointing to the CPU memory. Right? In contrast is the deep copying, where if you have a CPU pointer pointing to a memory location on the CPU and you do a deep copying, then you create a copy on the GPU of the pointer, and you also create a copy of the memory location which that pointer is pointing to, and let that GPU pointer point to that GPU memory. Right? So then that is called as a deep copying, and this you can recursively do. For example, the pointer might be pointing to a structure which might have another pointer which might be pointing to another structure, and so on. So there might be, for example, you can think about a tree or a graph, and you are given just the root. And if you do a deep copying of starting from the root, then essentially the whole graph or the whole tree is going to get copied, because it is going to go deeper into the pointers and copy that memory also and update the pointer pointer's value, which is the address of the memory location appropriately. So that seems to be desirable in general, but that doesn't happen, at least in the PGCC compiler. So I'll show you this little pictorially for the benefit of everybody who don't understand it fully, right? So OpenACC performs shallow copying of pointers, and that means that the pointer within a structure is only copied. So structures you can copy arbitrarily, there is no problem. If it has only scalar values or even arrays, that is okay. Or it can have another structure also within itself, that is all okay. But the pointers will cause some problem. For example, if this is CPU memory, which has a structure which has three different elements. One is the integer, second one is a character, and third one is a pointer. And let's say that pointer is initialized to some memory location which is also on the CPU memory. Right? So in case of, when you want to copy, in case of deep copying on the GPU, you want that copying in should create a structure which is exactly similar to the CPU memory. So this is desired, but what actually happens is shallow copying, where you have this 5 and x copied because these are scalars, but the pointer still points to the CPU memory, and that is wrong. I mean, wrong meaning that is the behavior. Now, if you are aware that this is what is happening, then you will implement deep copying yourself, or maybe you will solve this problem in a different way. Maybe you will not use pointers. Maybe you use, let's say, convert it into arrays and so on. Right? For example, you can copy this red memory location directly here, and then do a copying, and then you will get another red memory location here, right, or here. So that is one way in which that can be done. But yes, you have to take care of deep copying. What this is what it means. So for example, just in this case, this is the structure, and then if I'm trying to access star of s.ptr, then that is going to cause an issue. By the way, on the CPU it will work very well. On the GPU, when you try, then it is going to cause an issue. So we have to be a little careful about that part. So if this access is invalid on the GPU, with a good chance there will be a seg fault on the GPU, and you might not get the expected behavior out of your program. But is there a way you can avoid this seg fault if you want to just identify whether OpenACC performs shallow copying or deep copying, right? So that is one homework which I want to give you, is that if you can write a program which doesn't crash, which doesn't give unexpected output, but it still validates that shallow copying is happening on the between CPU and GPU because of OpenACC copying. Please think about how you will write this program. Okay, so we have already exceeded the time, but that's okay. Yeah, I don't think I have anything more to do. This completes our discussion on various constructs which are primarily available for writing most of the codes. What we are going to do tomorrow onwards is to write actually these different codes. And since vectors and matrices are useful in multiple domains, we are going to start with those. Tomorrow we'll look at different operations, different let's say programs which make use of vectors, and then hopefully the concepts are going to be similar for optimizing the data transfer, for parallelization, etc. But that will also give us some exercise or practice with respect to different vector related operations, because in the first class there was also this question that will we have any practice sessions. Although we won't have any specific practice sessions, these next three classes are going to actually help us practice, because we'll do lots of different kinds of problems into this. Conceptually these are going to be, I mean, the whole idea behind OpenACC is to make it easy for you to code this up. So I think that you will see repeatedly in different vector operations as well as different matrix operations. So we'll do that tomorrow onwards. So that completes things from my side for today. If there are any questions or concerns or discussion, we can have that now. Okay, so I don't see that there are any questions as of now. So I'll wait for some more time. I'll stop the recording now. And in case